Chronic Kidney Disease Prediction, presented by Wilfred, Anne, Rosita, and Crystal. The prevalence of chronic kidney disease imposes a significant challenge globally. The disease is affecting 13% of the world population, and the widespread occurrence of CKD requires a proactive approach to predict and manage potential kidney-related issues. Early detection of CKD produces better outcomes by decelerating the process to end stages. As businesses and governments deploy artificial intelligence to navigate evolving challenges, our initiative aligns with this forward-thinking approach to address the complexities of kidney health. By leveraging statistical and machine learning techniques, we aim to build a predictive model capable of forecasting the likelihood and types of kidney problems. Our project has 4 objectives. Number 1, employment of multiple machine learning techniques. Our study is focused on utilizing a diverse array of machine learning methods, including logistic regression, linear discriminant analysis, class validation, tree-based classification, and decision tree models. This comprehensive approach is aimed at analyzing and modeling the dataset effectively. The second objective is development of predictive models. The core goal is to develop robust predictive models through these techniques. By doing so, we aim to enable precise forecasting and gain insights into the dataset's behavior, facilitating informed decision-making processes. The third objective is performance assessment across various metrics. An essential part of our study involves evaluating the performance of these predictive models using different metrics. This evaluation will help us understand the efficacy of each model and its suitability for the dataset, ensuring we choose the most effective approach. Number 4 is the investigation of model interpretability and feature importance. We aim to not only identify the most suitable method for the given data, but also delve into the interpretability of the selected models and the importance of features within them. This exploration will enhance our understanding of the underlying patterns in the dataset, providing valuable insights for informed decision making.
The dataset that we will be using came from the UCI Machine Learning Repository and is licensed under CC 4.0. The data was collected from a hospital in India over a 2-month period. The dataset contains 25 features and 400 records. There are 11 numerical data types and 14 nominal data types. For data cleaning, phase 1 will be dealing with variables. We first renamed the feature names to be more understandable. The next step was to change certain nominal data types to numerical. We changed some of the classification features from verbal descriptions to 0 and 1. This was done to convert our variables into an easily manageable data type. Finally, for phase 2, we dealt with the null values. This was done in 2 ways. On numerical features and nominal features that had a large number of null values, we used random sampling to repopulate the data. On nominal features that had a small number of null values, we filled the blanks with the mode of that feature. All of our data cleaning was done with Python and then exported to a CSV file for use in R. To examine the data and gain insight into the context, we visualize the data using Python. In summary, the features of the sample appear to consist more of healthy individuals, while a smaller portion seem to have some health issues. The observation is supported by the bar chart, which indicates that more people are classified as 0, meaning they have no chronic kidney disease. We also generated a correlation matrix of features to help identify correlations between the features and the class label. Although some features exhibit slightly higher correlations than the others, during a later stage of our analysis, we checked the VIFs of the variables and found no multicollinearity issues. A high pairwise correlation between two variables does not always result in high VIF, as the VIF evaluates the combined effects. of multicollinearity among all predictors in a regression model, not just individual correlations.
Methodology. For the prediction of kidney disease, we have a large number of categorical and numerical explanatory variables, and the numerical explanatory variables primarily have discrete values. Logistic regression, Bayesian boundary, and tree-based algorithms are among the options considered due to the categorical response variable. For logistic regression and boundary classification, generalized linear model is not suitable for capturing complex nonlinear relationships and has a lower accuracy if relationships are nonlinear. For the linear discriminant analysis, it assumes identical covariance matrices for each class, and the performance may suffer if this assumption is violated. For the quadratic discriminant analysis, it allows for class-specific covariance matrices and is more flexible but prone to overfitting with small datasets and a higher computational complexity. For classification tree and random forest, the classification tree splits data based on features, forming a tree structure using if-else rules. Prone to overfitting, and especially with D trees, leads to high variance. For the random forest, it constructs multiple trees and averages or votes their predictions. And it's less prone to overfitting, reducing variance, and sacrifices interpretability for better performance. And it requires more computational resources and longer training times.
Hey everyone, Ans here. I'm going to talk about logistic regression, linear and quadratic discriminant analysis, and random forest, which I just learned a bit about yesterday. First, I try to fit the logistic regression model with our explanatory variable result in none of them being significant. After removing all category variable and refitting the model, 4 variables are significant. No collinearity was detected in all the explanatory variables. Stepwise algorithm yield model with 6 variables. So I performed 10-fold cross-validation with 3 repeat to select between the model from the stepwise algorithm and the model with 4 highly significant variables. The accuracy rate from cross-validation is very close for both models. So I decided to use both models to predict and see that they actually yield the same misclassification error. So I decided to select the model with 4 variables because it has 0 false negative and it only has 4 variables. Now let's look at LDA and QDA. LDA has a slightly higher misclassification rate but has no false negative, while QDA has 1. Later we will perform cross-validation to confirm this. Partition plots show the quadratic boundary of QDA does not improve much accuracy since the response variable exhibit cluster pattern. Alright, now let's look at random forest. The tree versus error plot suggests that minimum number of trees that yield the lowest error is about 40. So 43 tests and result in 0 misclassification error. The 3 examples show a mixture of the categorical and numerical variable on the nodes. The mean decrease Gini table indicates the 4 variables selected in the linear regression model also have a high importance for this model.
We have done the tree classification with all the variables, and our method selected the serum serotonin, a specific gravity, blood urea, and hemoglobin as the main variables to construct the tree. As you can see on the right hand side of my slide, we also have done the cross validation error versus the tree size. And as you can see, we have like 2 candidates as the best size, 3 and 4. We examined both, and we noticed that the size 3 is basically increasing the misclassification rate. So but the size 4 is not improving it. It's still 0.025, but we decided to keep the size 4 and to keep the misclassification rate as 0.025. So the last one on right side of the slide, you can see the prone 3 with the accuracy rate of 0.975. We also have examined different methods like LDA, QDA, logistic regression, and classification tree via cross-validation, and we got different accuracy. For LDA, we got 0.92225, for QDA 0.9555, for logistic regression as well the same 0.9555, which both are better than LDA, and the classification tree with three different results, which we are selecting the optimal model using the largest value of accuracy, which is 0.96, and the CP of 0.04. Thank you, and now Alistair will continue our analysis.
Let's look at our models as a whole. Starting with the worst performing model, the linear discriminant analysis achieved 92% accuracy. Although this is great, other models have performed better. The quadratic discriminant analysis had a higher accuracy of 95%, and this makes sense because QDA is more flexible than the traditional LDA. Next, our logistic regression model performed similarly to the QDA with about 95% accuracy. And amazingly, the random forest model was able to predict chronic kidney disease with 100% accuracy. This was, however, our most computationally intensive model. Finally, our classification tree was the next best performing model with a 96% accuracy. In conclusion, our tree models performed the best. These tree models tend to have two main benefits. They tend to be more suitable and robust towards datasets with a mix of categorical and numerical variables, and they are much less impacted by multicollinearity. Since our dataset was fairly large, moving forward with a tree-based model makes the most sense. And of our two tree-based models, the random forest model performed the best with 100% accuracy. As for the application to diagnosing chronic kidney disease, it must be noted that our models were developed for research purposes. This means that they require further testing and iteration before they could be considered for real-world healthcare applications. However, this does show promise for growing the influence of statistical learning in healthcare. Thank you for watching.